Spectroscopy is the study of light, and now that we've seen how black bodies emit a continuous spectrum, we can recognize that we can study the details of the intensities of light at various colors and learn things about that body, namely its temperature, and we can determine its color. Well, there's more to spectroscopy than just looking at a continuous spectrum. There's also something called a line spectrum that is produced when a gas is very hot. So if you take a flame and dump chemical into the flame, it produces gases, and they emit photons of specific wavelengths, as can be seen in this graphic here. Bright lines show up on the screen after the wavelengths are spread apart through a prism. And so that tells you, turns out, the composition of what it is that you're putting in the flame. Another way to spread out the light is with a grating spectrograph. So if you put a light through a slit and have a mirror, you impose that white light upon a grating and it separates it into the various colors, and you do the analysis. So we're not focused on the technology here, but on the basic science. And what's shown here is a spectrum of the sun, in part at least. And you can't tell the colors, but it turns out the wavelengths are increasing in this direction. What's interesting about this is you see all these absorption lines. The absorption lines are from the gases in the atmosphere of the sun with a very hot sun behind them. It turns out that those elements in the sun's atmosphere are absorbing some of the photons, and that's causing these notches in the spectrum. Otherwise, this would be a continuous spectrum. So, this is the spectrum of the sun with the absorption bands. And what we see below that is the emission lines for iron that can be discovered in a laboratory. And with using this method, if we vaporize iron, it produces lines on a screen corresponding to these lines, as shown here, various wavelengths. So this is the emission line spectrum for iron. Notice, interestingly, that each emission line is matched up with an absorption line on the sun. What this tells us is that the sun actually has iron in its atmosphere, and that atmospheric iron is absorbing the photons that are the continuous spectrum, the black body spectrum, which is the photosphere of the sun itself. So, in brief, a hot gas emits lines while a cool gas absorbs lines, and those lines are evidence for photons at different wavelengths. So let's develop this just a little bit more. This light emission and absorption phenomena can be summarized with what's called Kirchhoff's laws of radiation. So it goes like this. The first law is that a solid, liquid, or dense gas acts like a black body, and based on its temperature, it emits light. When it's sent through a prism, it reveals that it's emitting a continuous spectrum, all the wavelengths. So there's law number one. We already discussed that. That's the black body. Well, if that black body radiation goes through a cloud of cooler gas, cooler than the black body itself, there will be something that happens in this cloud. Namely, the atoms will selectively absorb some of the photons coming from this continuous spectrum of all the wavelengths. Specific wavelengths are absorbed. The wavelengths that are absorbed can be seen here as the absorption lines. And so law number two, with the cloud of cooler gas in front of the black body, in front of it, is that a hot object shining through a cooler gas, that would be the hot black body, produces an absorption spectrum. And then this same cloud is warmer than the background here, and there's no hot body in back of it, so it now is considered a warm cloud, and it actually emits light that goes through a prism, and that light is spread out, and it reveals an emission line spectrum. So that's the same phenomena as the flame, the material put in the flame, vaporize the material, and producing emission lines. So an emission line spectrum is produced from that. So law 3, a thin, warm gas by itself produces an emission spectrum. So there it is, and we'll look at an example and then a little bit more as to why in the world this happens. What's going on at the atomic level? So here's the example, hydrogen gas, and we're showing emission and absorption. Hydrogen gas, again, is the most prevalent atom and molecule in the universe. And in the first picture, we see an absorption spectrum. A hot object is shining through hydrogen gas. If that happens, then we see the intensity and the wavelength. So you see notches here. The notches in the intensity correspond to these black lines. That's the absorption. So the hydrogen gas is absorbing these photon wavelengths specifically. On the other hand, if the hydrogen gas is warm and it's by itself, it actually emits photons, and the photons it emits are at the same frequencies or wavelengths as the ones that were absorbed, and we produce an emission spectrum. So there's a reciprocity here. Hot body, hot object, hot black body through hydrogen gas absorbs, the gas itself emits. So what is it about atoms that produce line emission or absorption? Let's check that out. Just a brief overview of atomic structure. Here we see an atom represented, and there's the nucleus and the electron cloud. 10 million atoms could fit across this little dot over here. The nucleus itself is 100,000 times smaller than the whole atom, which is only 10 to the negative 10 meters, a tenth of a nanometer. The nucleus is very, very small, but contains almost all the mass. A proton is 1,836 times the mass of an electron, and the nucleus contains protons and neutrons. Well, just to get an idea about the scale of an atom, if you could take the nucleus and put it in the center of a football field. Now it's invisible because it's a grapeseed in size, not as big as my laser pointer, just an invisible dot there in the center of a football field. Well, this is the size of the atom, several hundred meters in diameter. So think of a sphere that big. That'd be a huge sphere. And you got a little dot right in the center where almost every bit of the mass is. Almost every bit. So you can see that an atom is mostly empty space. The empty space, though, is taken up by this electron cloud. Now, the electron cloud is not little orbits like planets. It's a little more complicated than that, but it is okay to think of it that way as a visualization. So regular matter is almost completely empty space. In fact, if you could take nuclear material, just take nuclear material and fill a teaspoon up with it. These grape seeds here, if it was pure nuclear material, a teaspoon would weigh 2 billion tons. Now that's like a mountain. Can you imagine a teaspoon of something weighing 2 billion tons? Well, I'll answer that for you. No, you can't. But that's the reality of nature. So the stuff all around us, the regular matter that we think is hard and solid, is almost completely vacuous, almost completely absent of mass. So it turns out that this electron cloud, as I said, isn't really little orbits of tiny little dots called electrons. They're smeared out and they have probability distributions as to where they are, and that's all part of the quantum mechanical nature of reality. But the key to line spectra that we're talking about is understanding that the energy levels of the electrons, wherever they exist in this cloud, are quantized. Namely, they have certain values and nothing in between. And because of that, we get absorption and emission of the line spectra emerging from that reality. Let's consider the energies that are possible in a hydrogen atom. This chart is showing the various possibilities. N is equal to 1 is the ground state, considered to have no energy. So that's 0 electron volts. Electron volt is a unit of energy. And as we progress up here, N is equal to 2, 10.2 electron volts, and then 3, 4, 5, 6, 7. And as infinite number of lines up to the very top where it converges at 13.6 electron volts. Those are the energy levels permitted in a hydrogen atom for the electron to have. Photon energy, as we've seen before, is related to Planck's constant, the speed of light, and inversely related to the wavelength, or it's equal to Planck's constant times the frequency. So the energy of the photon is proportional to frequency, inversely proportional to wavelength. The transitions between levels, from one level to another, actually correspond to energy level differences for photons, either absorbing or emitting. The energy level for the electrons are quantized, which just means that there are those specified energy levels. Ground state, the first excited state, the second, third, fourth, fifth. You can't have an energy level in between any of these two states, any of these two orbital energy levels. So it's like a ladder versus a ramp. You just got one rung, and then if you want to have more energy, you go to the next rung, and you're really not permitted to have anything in between those rungs. So nothing in between, only those certain levels. Too much input energy ionizes the atom. So if you put more than 13.6 electron volts in, you have ionization. It knocks the electron clear out of the atom. That's what ionizing is. So we can have either absorption, we can absorb a photon, in which case it knocks the electron up to a higher energy level, or the electron can emit a photon and drop to a lower energy level. And the energy of the photon is the difference in energy of the transition it's making. But let's look at another graphic to make this a little bit more clear. Now there's not a whole lot to understand here, so hopefully this picture will make it clear. So here we have the atom with the various energy levels, ground state, n is equal to 1, 2, 3, 4, etc. And we have photons coming in from the outside, and they are impinging upon the atom, and those different wavelength of photons, if they're just right, they will cause an electron transition. So the electron can be kicked into a higher state from 1 to 2, from 1 to 3, from 1 to 4. It also can do other transitions, intermediate ones, if the photon has just the right energy. So if it does, the photon's absorbed, the electron is in an excited state. So what is that special energy of the photon? Well, this photon right here has got an energy, if it has an energy equal to the energy of level 3, it's the third level, minus the energy of level 1, that's the difference in energy between these two levels. That's just the right amount of energy to kick it from level 1 to level 3. See, it's very logical. This one is the energy of level 4 minus level 1. Notice it's a shorter wavelength photon, and it'll kick it from 1 to 4. All of the photons pass through unabsorbed because they have the wrong wavelength, therefore the wrong energy, and nothing happens. So that would be most photons. They'll just pass right on through. So here's an example, hydrogen alpha line, as it's called. So we have a black body somewhere emitting a continuous spectrum, and one of those wavelengths is 656.3 nanometers, and it's just the right amount of energy to kick an electron from level 2 to level 3. Fantastic. It absorbs the photon. Then it turns out that nature loves lowest energy situations. They don't like to remain in high energy conditions. So the electrons will spontaneously transition back, and when it does, it goes from level 3 to level 2, which is the same amount of energy transition, and it will now emit a photon of that exact same wavelength. And that's how we get an absorption line and an emission line at the same wavelength, respectively. Well, because spectroscopy is so foundational in astronomy, and because the hydrogen atom is so ubiquitous in nature, I want to take one more stab at explaining this. And here you see a hydrogen atom, a little bit more to scale and size and energy level perspective here. So it'll make this a little more visual perhaps. Well, the most prominent lines in many objects in astronomy are the Balmer lines of hydrogen. Here they are. It's a series of lines, and they're kind of special. And here is the photon energy formula once again, just for background. They're special because they're very important for studying stellar processes and understanding compositions and relative abundances of hydrogen gas and other things going on out there. And they involve transitions to from energy level 2 and from to higher levels. So here we see level 2, and here's the higher levels. So if it's from a higher level to level 2, it's emitting a photon, and it'll absorb a photon if it's from energy level 2 to a higher order level. So that's how that works. These are the Balmer lines, and they're special. They're special because of the wavelengths you see here. What do you notice about the wavelengths? 656 on down through around 400. Where does that lie? Well, you might realize in the word here, it's visible. And so they're kind of special for us. And so here is the emission lines for the Balmer series. And then, as I just described, if photons are coming in and they're absorbed, produces the absorption line. Hydrogen gas produces an absorption line like this as a result of a black body shining through the gas. There's also the Lyman series, to from level 1. So here's level 1. Notice that these lines are a lot longer. That means they're higher energy. And because they're higher energy, they're shorter wavelength. And because they're shorter wavelength, they're no longer visible. Not in here. In fact, they're to the left of this. It's ultraviolet. In like manner, we have the Passion series, to from level 3. Well, those are tiny little energy transitions. So small that the wavelengths are much larger, and it's beyond the red, infrared, and those are important but not visible. Most energy transitions in hydrogen and in other elements and molecules and are essentially non-visible. It's very unique when you have the energies being just right so that you can actually see them, part of the visible spectrum. At the risk of boring you to tears, here's a somewhat cartoonish visualization of the process. So we have a random photon coming in to this atom, and if it's random, it probably won't be the right energy level. So the atom says, sorry, I don't think I like you. You're not my type. But this particular photon has got just the right amount of energy to take it from the ground state to an excited state. So then the electron says, thank you very much. And it gets all excited and wee as it zooms around in an excited state. But in the human realm, little kids that get excited, which they're wont to do, they can't stay excited that long, right? They get tired and all of a sudden collapse. And that collapse is analogous to the electron jumping from the excited state down to the ground state again and emitting a photon of the same length that it absorbed in the first place. Here are Kirchhoff's laws in a nutshell. So we have the hot black body source producing a continuous spectrum. A gas cloud that's between the source, on the other side of the source, or in front of it, I guess you might say, absorbs through upward transition of the electron those wavelengths that are just the right energy level, and you get an absorption band. And then the gas cloud itself, because it's got those same atoms in it, some of the electrons which are in excited state will spontaneously transition down to a lower state and produce that same photon, but this time it's an emission photon. It's producing the photon rather than absorbing it. And there's the entire process. And hopefully all these explanations have come together to produce understanding in your mind. So let's check out how this works for the sun. So here's the sun, a hot black body interior, continuous spectrum. the photosphere is producing. The cooler atmosphere absorbs certain photons because of the constituents of the atmosphere. Then that goes on over to an astronomer on Earth that's observing that spectrum, and the astronomer sees these dark absorption lines. And here's a little more detail about those dark absorption lines. There is a lot of them, but there's even more than that, as you'll see in the next slide. This is it. This is showing an extremely spread out spectrum of the wavelengths, all the way from infrared up here, all the way through, stacked one on top of each other, to blue and violet and going to the ultraviolet. Now notice how many, it's almost uncountable number of absorption bands. This image actually shows several thousand. There have been about 30,000 absorption lines found in the spectrum of the sun, corresponding to 90 some elements in the atmosphere. So it's amazing how much information about the constituency of the sun and the relative proportions even that we can obtain from such a detailed spectra of the sun. Some of the objects we see in astronomy are so beautiful because of this downward transition of the electrons in hydrogen atoms. And this is a case in point, the Cocoon Nebula in Cygnus. It's an emission nebula. It consists of a whole bunch of atoms of hydrogen that are in the excited state, and as the electrons transition back down to a lower energy level, they emit that hydrogen alpha line, which is the red emission line in the Balmer series. And so we have a beautiful nebula of this reddish color, and so that's seen often in various places in our galaxy and other regions where we can see nebula that are lit up because of these electron transitions. Here's another example, and once again it's the hydrogen alpha emission line in this planetary nebula, which you don't need to know what that is yet. And we even have a different color. We have a greenish in here, which is typically from ionized oxygen. So it has its own emission spectra as a result of the downward transitions of electrons from an excited state down to a lower state. And finally, this is one of my favorites. It's the Witch Head Nebula, and this turns out to be Rigel, one of the bright stars of Orion. And here's the witch, and nose and mouth, eye socket. So that's kind of cool. It looks like the witch is trying to consume Rigel or something. But more to the point of the science, this turns out to be a reflection nebula. It's not an emission nebula. It's kind of like why the sky is blue. So the light you see from it, the bluish light, is a result of basically scattering the blue light from this bright star Rigel, as opposed to the atoms in the gas itself emitting light as a result of the downward transitions we've just been describing. So there is a little bit on spectroscopy, and we will move on to the next topic.